All right, everyone. So these are the examples that go along with the lecture from before. We already did some simple examples, and we saw how angles can affect the amount of work that a force does. So even though the force, uh, the magnitude of the force can remain the same, that by changing the angle, we can see different effects from that. So in example number one, we have our angled force, all right? And we'll see what happens here. So you should either have the handout or you will find it on the Moodle page, and you can follow along. So we have a horse pulling a carriage, and we're going to say in this case that there's not going to be any friction. It applies a 200 Newton force at an upward angle of 15 degrees for a distance of 100 meters. So what is the work done by the horse's force? All right. So the first thing that I want to do here is actually draw a diagram of what's happening in the situation. All right. Here is the carriage. All right. And there are forces that are acting on this carriage. So the horse's force, all right, is directed at an upward angle of 15 degrees. So this is the force that we're talking about, and this is the angle that we're talking about. All right. Now the horse is actually pulling the carriage in my picture off to the right, and so that's going to be the direction of my positive x-axis. We're going to see later how this direction can change. All right. So I have this force of 200 newtons. All right, I have this angle of 15 degrees. And the other part of this that I see is that the object moves a specific distance of 100 meters. So these three things together are enough to help us calculate the work done by the horse's force. So we're going to use FD cosine theta. All right, so our force is 200 newtons. All right, we have our distance of 100 meters. And then we have the cosine of our angle, which in this case is 15 degrees. All right. And when we calculate this, we're going to get what seems like a really absurd number. So go ahead, punch that into your calculator. Don't be lazy. You can do it. 200 times 100 times the cosine of 15 degrees. And we get, holy cow, 19,318 joules. I'm not even going to bother writing the decimals on that because that's such a huge number. Who cares about the decimals on that? So that might seem wrong to you, but here's the thing. A joule's worth of energy really isn't that much energy, and so we're going to see some really, really large numbers. Often what you'll see is that we will write these things in kilojoules instead. So this would be more along the lines of 19 kilojoules, all right? And that's because we typically deal with a lot of joules. So this might be like 19.32 kilojoules. And so often what people do is ask the question like, all right, when do I use kilojoules? When do I use regular joules? My threshold is around about 1,000 joules, and I start to write things as kilojoules. All right. It wouldn't be wrong to write 19,318 joules. That's the same thing. But, you know, when we start to get hundreds of thousands of joules and, you know, millions of joules, then we're not going to really want to write it that way. All right, so off to our next example. So what happens when we have multiple forces that are acting on an object? Well, we see that each one of these forces is doing a specific amount of work. So we have a 15 kilogram box, and it's being pushed 3 meters along the floor with a force of 25 newtons at 30 degrees. All right. So if the force of friction in the picture is 2 newtons, calculate the work done by the applied force, the force of friction, the weight, and the normal force. So we should be able to calculate the work done by each of these 4 forces. And we're going to be able to use some things that we saw in our lecture notes to actually help us out. All right. So the 30 degrees is right down here. We're pushing at that downward angle of 30 degrees. All right. And let's start calculating um, some of the work that's being done. So I'm going to call this work A. And that's going to be the work done by force A. All right. So that will be force A times the distance times the cosine of the angle for A. All right. Well, if this is 30 degrees right down here, then we know that our standard angle, okay, is going to be what? So think about it. We should get an angle of 330 degrees for that force. All right, so that's what we're going to use for force A. So force A here is 25 newtons, all right, times our distance of what? 3 meters times the cosine of 330 degrees. And we get the work done by force A. So go ahead, again, punch it into your calculator. And we find here that the work that's been done by force A is 64.95 joules. So in this case, I'm not going to use kilojoules because 64 is a small enough number. If we were up in the thousands or tens of thousands of joules, then I'd switch off to kilojoules and keep a couple decimal places. All right. So this is the work that's just done by force A. This is not all of the work that's being done because other forces are doing work too. If we have this thing moving off to the right, okay, I'm going to erase some of the stuff here on our picture. Let's look at the force of friction here. All right. So friction, if we're moving off to the right, okay, then friction is pointed off to the left, and I'm going to use a standard angle of 180 degrees for that. So we can do the work done by friction, all right? And so that would be the force of friction times the distance times the cosine of the angle for friction, all right? So the work for friction here, we have a 2 Newton frictional force, a distance of 3 meters, times the cosine of 180 degrees, all right? And so we get the work that's done by friction is a negative 6 joules. So here's the deal. The applied force is increasing the energy or adding 64.95 joules worth of energy to the box, whereas friction is taking 6 joules of energy away from the box. So we got one force that's putting energy in, and we got another force that's taking energy out. And so we're going to see this with all different types of forces, that depending on what direction they're pointed, they're either going to be putting energy into the object or they're going to be taking energy away from the object. Now what about these other two forces? I am not going to do these calculations. Why am I not going to do these calculations? It's not that they don't have a value. I know exactly what the answer is. Like for the normal force, for example, the work of the normal force, I'll call it double Wn, just like that, has to be 0 joules. And so does the work of the gravitational force, I'll call that Wg, also has to be 0 joules. Why? Why? All right, if I'm moving off to the right here, then that means that the normal force is at a right angle. It's perpendicular. It also means that the gravitational force is at a right angle. It's perpendicular. And we know that forces that are perpendicular to the direction that we're moving don't do work. So do I have to do that calculation? Absolutely not. Absolutely not. All right. So I get 0 joules worth of work for the normal force and 0 joules worth of work for the gravitational force. So when you have multiple forces, they are all doing work. I can add all of these up and find the total work that's being done on the object. All right. So it'd be 64.95 joules plus negative 6 joules plus 0 joules plus 0 joules. And that'll tell me how much total work is actually being done by all of the forces. Let's look at example number 3 here. So we have a weightlifter, and they're bench pressing a barbell that has a mass of 55 kilograms. All right, so he raises the barbell at a constant velocity, a distance of 0.65 meters above his chest, and he lowers it back to his chest the same distance. So let's determine the work done on the barbell by the weight or the gravitational force during both the lifting and the lowering phases. So here is where direction matters, all right? So let's say I have a barbell, all right? And so let's say this is my weight, all right? 55 kilograms worth of mass. When I lift this weight up, all right, then what direction is it moving? It's going to move in the upward direction. So that's the direction of my displacement this time. And that's the direction of my distance this time. All right, so I'm going to raise it up 0.65 meters. On the way back down, it's going to start up here at the top. All right, and now it's on its way down, so my displacement is in that direction. And that's the direction of my distance. So how does this affect things? Well, this is going to change the angle theta in each of my situations. So we're looking at the gravitational force, all right? And that's Fg, just like this. And so I can draw it in both of these pictures. So what is this actually going to change? This is going to change the amount of work done by the gravitational force in each case. So during the lifting phase in our first picture, all right, since we're displacing upward and we have a downward force of gravity, what's that standard angle? Well, this standard angle, theta, is 180 degrees. So when I go to calculate the work that's done during the lifting phase, all right, so I have my force times my distance times the cosine of my angle, right? So what's the force that we're talking about? We're talking about the gravitational force. All right, so we have 55 kilograms with an acceleration of 9.81 meters per second squared. And so we have 539.55 newtons worth of force. We have a distance here of 0.65 meters. And we have a cosine of our angle theta, which is 180 degrees. So look at these numbers that we're plugging in here. All right, 539.55. Notice that I do not have a negative on that. And the reason is that that has to do with completely different stuff. All right, up, down, left, right, not negative in these cases. What makes something positive or negative has to do with the standard angle. So because we're displacing upward, but our force is pointed downward, we have a theta of 180 degrees. And in this case, right, we can go ahead and calculate. And what do we find? During the lifting phase, gravity is doing negative 350.71 joules worth of work. So on the way up, gravity is working against you. It's actually taking energy away during this situation. So you're pushing up and gravity is pushing down, and so you might be putting 350.71 joules in, but at the same time gravity takes 350 joules worth of energy out. All right? So what changes in the second part? Well, the standard angle changes in the second part. When we lower this barbell back down, all right, now our displacement is in the downward direction. Okay? And so is the force of gravity. And so the angle between those two is going to be 0 degrees this time. And the only thing that changes in my equation is the angle. So now we have cosine of 0 degrees. And what do we get? Well, same number, just positive. So now we have a positive 350.71 joules worth of energy. So on the way down, gravity is actually doing work, adding energy to the barbell, and as we push up, we're taking energy away from that barbell, the exact same amount. So we can see that right is not always positive, up is not always positive, all right? Sometimes down is the positive direction, and that's where we're taking our standard angle from. So the standard angle always comes from the direction that you're moving or displacing, not up, down, left, right kind of stuff. All right, so you have to pay attention to the direction that you're moving. That's what's going to help you with theta. All right, so let's take a look at a few conceptual questions. So in the first conceptual question, we say, can a force do work even if the object doesn't accelerate? So let's think about that for a second. If you want to, you could even pause the video, right? And go do 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 Do, 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 do. All right. So can a force do work even if an object doesn't accelerate? Yes. The answer is yes. All right. So acceleration is not the requirement. Remember, forces do work as long as one of two things is true. As long as there is a force, and as long as that force is pointed in the same direction that it's moving, the object moves. All right? So the object needs to move. All right? So it has to go a certain distance. All right? And the force has a parallel component to the motion. Then we know that it's going to actually do some work on the object. All right. So acceleration isn't required. We just need a force. All right. The object needs to move, and that force has to be pointed somehow, have a component that's parallel to the way that you're moving. All right. Otherwise, if it's perpendicular, it's not going to do any work. All right. So let's look at the second one. True or false, vertical forces don't do work. All right. Well, hopefully you didn't just forget this previous example that we did, because clearly we have two vertical forces here, the gravitational force that is doing work. But we have this example where the vertical forces are not doing work. So we can immediately say there's no way, this has to be false. All right? This has to be false because we have examples where vertical forces are doing work. All right? But we also have examples where they're not doing work. So what's the explanation here? All right? It's not about vertical forces. It's about perpendicular forces. So if we were to change this, all right, so that it would be true, what would we change about it? Well, I'd scratch this word vertical. All right? In fact, I'll scratch all of vertical forces. And here's what I would replace it with. All right? Forces that are perpendicular to the displacement don't do work. All right? So it's not vertical forces. It's ones that are perpendicular to the displacement. So there's at least one example that we have where they are vertical forces and they don't do any work. But what about something like this? All right? So in this case, all right, we have a number of forces that might be acting on our box here, right? Maybe we have an applied force up the ramp. We have the normal force here, just like so, and we have the gravitational force pulling straight down. So what's what? Which ones are doing work? Well, the applied force is doing work. Why is that? Let's say this thing is going up the ramp, all right? It has a parallel component to the displacement. Gravitational force is pulling down and away against this thing, but guess what? Look, it has a parallel component to that motion. What force isn't doing any work? The normal force. The normal force is perpendicular to the motion up the ramp. And so it's not doing any work. All right. So there are numbers of examples here where we see that things, um, if you're not careful, that you can get caught. All right. So true or false, negative work means that the force is to the left or down. Oh, don't you dare make this mistake. What does negative work mean? No, negative work means, right, that, here, we'll leave this part, that the force is taking energy away. All right? It's taking energy away. It is not about direction. All right? Work does not have direction. It's not up, down, left, right. It's either work where you transfer energy in or you transfer energy out. Those are your only two choices. But that's what positive and negative mean for work. All right, guys, this is all the basis for everything that you'll need to know for this section. All right, you'll now go ahead and complete the homework assignment that goes along with this, and then you'll take those answers and you're going to enter them into um, what's labeled as a quiz there, but it's the work homework answers quiz. So you're going to enter your actual values into that thing, and it's going to check it for you. You'll get 3 chances to get all of them correct, whatever your final answer is at the end or whatever your final number correct is, that's going to be your score in the grade book. All right, guys, good luck. And if you have any questions, make sure you are using the forum that's online. You can ask those questions there. Have a great day.